Determine whether the series converges or diverges. Let's take a look at example 1. Suppose we have the summation from n equal 1 to infinity of n plus 1 over n to the third plus n. A sub n is n plus 1 over n to the third plus n. So I'm going to apply the limit comparison test. So I need a suitable candidate for b sub n. Now, to get b sub n, I'm going to write the following. In the numerator, I'm going to write n. And where do I get that? When I look at a sub n, the term with the highest degree in the numerator is n. Now, in the denominator for b sub n, I'm going to write n to the third, right? Why? Because if I look at a sub n, the term with the highest degree in the denominator is n to the third. So that makes a suitable choice for b sub n. My choice will be n over n to the third. But if I simplify that, I get b sub n is equal to 1 over n squared. Now, this is where we go next. I'm going to look at the limit as n goes to infinity of a sub n divided by b sub n. But that's the limit as n goes to infinity of. Now, the numerator will be n plus 1 over n to the third plus n. The denominator will be 1 over n squared, right? So, this is the limit as n goes to infinity of, the denominator is n cubed plus n. The numerator is n squared times n plus 1. Now, what I want to do is distribute the n squared inside. So this is equal to the limit as n goes to infinity of. Now, if we look back, right, I'm going to distribute the n squared inside to each term within the parentheses. So I get n to the third plus n squared divided by n to the third plus n. Now, I want to give you guys a slick way to evaluate this limit. Now, what I can do is the following. I'm going to take the limit as n goes to infinity. Now, I'm going to factor out an n cubed in the numerator. When I do, I get 1 plus n squared divided by n cubed. And I'm going to factor out an n cubed in the denominator. And when I do, I get 1 plus n over n cubed inside the parentheses. Now, the n cubes can cancel. And so this is the limit as n goes to infinity of 1 plus 1 over n divided by 1 plus 1 over n squared. Now, as n goes to infinity, 1 over n goes to 0. And as n goes to infinity, 1 over n squared goes to 0. And so this is 1. What does that say? Well, the summation from n equal 1 to infinity of 1 over n squared converges by p series. P is equal to 2, which is greater than 1. Therefore, the summation from n equal 1 to infinity of n plus 1 divided by n cubed plus n converges by the limit comparison test. And that's example 1. Let's take a look at example 2. Suppose we have the summation from n equal 1 to infinity of sine of 1 over n. And once again, I'm going to apply the limit comparison test. Now, my a sub n is sine of 1 over n. My b sub n is 1 over n. if I look at the limit as n goes to infinity of a sub n over b sub n, that's going to equal the limit as n goes to infinity of sine of 1 over n divided by 1 over n. And I claim you're going to get 1. And this is where you would want to ask your instructor if your instructor wants you to verify that that's 1. But I will tell you that you will get 1 from this limit. Now, what does that mean? The summation from n equal 1 to infinity of 1 over n diverges by p series. P is equal to 1, which is less than or equal to 1. Therefore, the summation from n equal 1 to infinity of sine of 1 over n, that's going to diverge by the limit comparison test. Example 3. Suppose we have the summation from n equal 1 to infinity of 5 plus 2n over 1 plus n squared. So I'm going to let a sub n equal 5 plus 2n over 1 plus n squared squared. So b sub n is n over n to the fourth. That's my candidate, okay? And if I simplify that, I get 1 over n cubed. Now, if I look at the limit as n goes to infinity of a sub n over b sub n, that's the limit as n goes to infinity of 5 plus 2n over 1 plus n squared squared divided by 1 over n cubed. And that's the limit as n goes to infinity of 5 plus 2n over 1 plus n squared to the second times n to the third over 1. That's the limit as n goes to infinity of 5n cubed plus 2n to the fourth divided by, and then I squared out the denominator and got n to the fourth plus 2n squared plus 1. So that's right here. And then what I did was factor out an n to the fourth from the numerator and an n to the fourth from the denominator. When I factor out an n to the fourth from the numerator, I got 2 plus 5 over n in parentheses. When I factor out an n to the fourth from the denominator, I got 1 plus 2 over n squared plus 1 over n to the fourth. Now, as n goes to infinity, 5 over n goes to 0. 2 over n squared goes to 0. 1 over n to the fourth goes to 0. And so, and by the way, n to the fourth over n to the fourth is 1, so those cancel. And so I'm left with 2. The summation from n equal 1 to infinity of 1 over n cubed converges by p series. P is equal to 3, which is greater than 1. So the summation from n equal 1 to infinity of 5 plus 2n over 1 plus n squared to the second converges by the limit comparison test. And does it make sense where I'm getting my b sub n? I look at the term with the highest degree in the numerator. Now that term is a 2n, and I don't need the 2. I do need the n, okay? And the term with the highest degree in the denominator will be n to the fourth. And that's how I'm coming up with my candidate for b sub n. Okay? Example 4. Suppose I have the summation from n equal 1 to infinity of square root of 1 plus n divided by 2 plus n. My a sub n is the square root of 1 plus n over 2 plus n. Now I need a candidate for b sub n. Now, if we look at the denominator of a sub n, the term with the highest degree is my n. So notice how that goes right here for the denominator of b sub n. In the numerator, for large enough n plus 1 is approximately equal to n. And so my numerator will be square root of n, right? Do you know what I said? for large n, n plus 1 is approximately equal to n. And so b sub n will be square root of n divided by n, which simplifies down to 1 over the square root of n. So that's my candidate. If I look at the limit as n goes to infinity of a sub n over b sub n, I get the limit as n goes to infinity of square root of 1 plus n divided by 2 plus n divided by 1 over the square root of n. But that's the limit as n goes to infinity of square root of 1 plus n divided by 2 plus n times square root of n over 1. But that's the limit as n goes to infinity of square root of n squared plus n divided by 2 plus n. So going right along. Now, if you look at this next line, I factor out an n from the denominator and get 1 plus 2 over n in parentheses. Now, inside the radical, I factor out an n squared. And when I do, I get 1 plus 1 over n inside the parentheses. And that's inside the radical, by the way. Now, remember, the square root of n squared is equal to n as long as n is greater than or equal to 0. So I don't have to have absolute value bars, in other words. So this is going to be the limit as n goes to infinity of n times the square root of 1 plus 1 over n divided by n times 1 plus 2 over n. And notice how these n's cancel. And as n goes to infinity, 1 over n is going to go to 0, and 2 over n is going to go to 0. And so that's equal to 1. The summation from n equal 1 to infinity of 1 over the square root of n diverges by p series. P is equal to 1/2, which is less than or equal to 1. And so that says the summation from n equal 1 to infinity of the square root of 1 plus n divided by 2 plus n diverges by the limit comparison test. Now, number 5 is very interesting. Notice how it's the summation from n equal 1 to infinity of sine squared of 1 over n. In an earlier example, we did the summation from n equal 1 to infinity of sine of 1 over n. So the summation from n equal 1 to infinity of sine of 1 over n, that one diverges. But now for this one, we have the summation from n equal 1 to infinity of sine squared of 1 over n. Okay, now I'm going to let a sub n be sine squared of 1 over n. My b sub n is going to be 1 over n squared. And then what I'm going to do is I'm going to look at the limit as n goes to infinity of a sub n over b sub n. So once again, I'm going to apply the limit comparison test. So this is the limit as n goes to infinity of sine squared of 1 over n divided by 1 over n squared. And this is the limit as n goes to infinity of sine of 1 over n times sine of 1 over n divided by 1 over n times 1 over n. And that's 1. And the summation from n equal 1 to infinity of 1 over n squared converges by p series. P equals 2, which is greater than 1. And so what that tells me is that the summation from n equal 1 to infinity of sine squared of 1 over n converges by the limit comparison test. And that'll do it for this video. It's 5 examples applying the limit comparison test. Okay, thank you.